All right, let's dive into one of the most essential skills in all of algebra, factoring. Now, if you know how to multiply polynomials, think of this as learning how to run that whole process in reverse. We're going to demystify this idea of unmultiplying and show you why it's such a powerful tool.
So, let's start with a little real-world puzzle to get us going. Imagine a landscape architect. They know the total area of a garden they're designing, but the formula for that area is this kind of messy algebraic expression. To actually start building, they need the simple length and width. So how do they get those?
And here's that expression for the area, x squared plus 5x plus 6. Right now, it might just look like a jumble of terms, but I promise you, the length and the width are hiding right inside that polynomial. Stick with me, and by the end of this, you'll know exactly how to find them.
To solve that puzzle, we have to learn to think backward. You probably remember how to multiply two binomials using the FOIL method, right? Well, factoring is literally just that process in reverse. We're going to start with the answer and find the original pieces that made it.
So what is factoring, really? At its heart, it's the process of unmultiplying. You know how division undoes multiplication with regular numbers? Factoring does the exact same thing, but for polynomials. It's how we break a big, complex expression down into its simpler, original building blocks.
This slide shows that two-way street perfectly. When we multiply, say, x plus 3 times x plus 2, we get x squared plus 5x plus 6. Factoring is the mirror image. We start with that x squared plus 5x plus 6 and work our way back to find the original bits and pieces, x plus 3 and x plus 2. Okay, so before we dive into the fancier methods, we've got to cover the absolute first step. This is a check you should do every single time. It will make your life so much easier. I'm talking about finding the greatest common factor, or as we call it, the GCF. So what is the GCF? Well, it's just the largest number or variable that can divide evenly into every single term of the polynomial. Think of it like tidying up before you start the real puzzle. Always, and I mean always, check for a GCF first. Let's see this in action with 4x squared minus 12x. First, we identify the GCF. For the numbers, 4 and 12, the biggest number that goes into both is 4. For the variables, we've got an x squared and an x, so the most we can pull out is a single x. So our GCF is 4x. Now we just divide each of the original terms by that 4x, and what's left over goes in the parentheses. And there's our answer, 4x times the quantity x minus 3. Simple as that.
Okay, now that we've got our first step down, it's time for the main event, cracking the code of trinomials. You know, those expressions with 3 terms, just like the one from our garden problem. And there are a few key techniques we can use.
Let's start with the most common kind of trinomial, where that first term is just a plain old x squared. The rule here is actually pretty slick. You are looking for 2 magic numbers, and these numbers have to do 2 things at once. They have to multiply to give you c, that constant number at the very end, and they have to add up to b, the number right in the middle.
Okay, let's try that rule out with x squared minus 7x plus 12. So we need 2 numbers that multiply to a positive 12, but they also have to add up to a negative 7. For that to happen, both numbers have to be negative, right? So we look at the pairs, negative 1, negative 12, nope. Negative 2, negative 6, still no. But what about negative 3 and negative 4? They multiply to 12 and they add up to negative 7, bingo. So our factors are x minus 3 and x minus 4.
Now sometimes algebra gives you a little gift, a shortcut, and this is a fantastic one to know, the difference of squares. If you see an expression that's just one perfect square being subtracted from another, think something like x squared minus 9. It follows a super predictable pattern. It'll always factor out to a minus b times a plus b. Recognizing patterns like this can save you a ton of time.
But what happens when that first term has a number in front of it, other than 1? Well, then we use a technique called the AC method, sometimes called factoring by grouping. First, as you see here, we multiply a and c, so 2 times 3 is 6. Then we find factors of 6 that add up to the middle term, which is 7. That's got to be 6 and 1. Now here's the trick. We use those 2 numbers to split that middle term into 2 pieces. Finally, we group the terms into pairs, pull out the GCF from each pair, and what's left reveals our final answer, 2x plus 1 times x plus 3. So we've covered the main ways to factor, but knowing what not to do is just as important. Let's look at a couple of common traps that can really trip people up so you can learn to sidestep them right from the start. Let's look closely at these 2 common pitfalls. First, the sum of squares. While the difference of squares, like x squared minus 9, factors out beautifully, The sum of squares, x squared plus 9, is what we call prime. It means it can't be factored using real numbers. It's a classic mistake to think it can. The other big one is just forgetting the GCF. You might look at an expression like this one and think it's way too complicated. But if you just pull out that GCF of 2 first, the trinomial that's left inside is suddenly way, way easier to solve.
Okay, we have officially built our toolkit. We know about the GCF, we can factor all kinds of trinomials, and we know which mistakes to look out for. So it's time to go back to the very beginning and finally solve our landscape architect's puzzle.
And here it is again. The total area of that garden is x squared plus 5x plus 6. Our mission? Unmultiply this expression to find the length and the width. We have the skills now. Let's get it done.
Okay, let's apply our simple trinomial rule. We need two numbers that multiply to our c value, 6, and add up to our b value, 5. So what are the factors of 6? Well, we have 1 and 6, but they add up to 7, so that's not it. What about 2 and 3? Do they add up to 5? Yes, they do. That means our factors are x plus 2 and x plus 3.
And there you have it. The dimensions of the garden are x plus 2 by x plus 3. Our landscape architect can finally get to work. By using factoring, we took a kind of abstract polynomial and turned it into concrete, useful information. The puzzle is solved.
So as you can see, factoring isn't just for finding the dimensions of a garden. It's a foundational skill for solving much bigger problems. We've learned how to break a polynomial down into its core pieces, but how can this exact same skill help us predict the path of a moving object, like figuring out exactly where a thrown ball will land? Well, we'll explore that next time.